We find ourselves in a room, a perfectly ordinary room. 4 walls, a floor, a ceiling. You can walk forward and backward, left and right, up the stairs and down again. 3 directions, 3 dimensions of space. Add the ticking of the clock on the wall, a 4th dimension, time, and you have described everything about where and when anything can exist. Or so you believe. This certainty feels like direct perception. 3 dimensions of space seem as obvious as the colour of the sky, as self-evident as the ground beneath your feet. We navigate these dimensions every moment of our lives, reaching for a cup of coffee, climbing a flight of stairs, catching a ball thrown across a garden. The very structure of our language encodes this understanding. We speak of length, width, and height as if they were the complete vocabulary of spatial existence. But here is the strange thing. Our confidence that 3 dimensions are all there are is not based on evidence. It is based on our inability to perceive more. And these are not the same thing. Consider what we actually know. We know that we can point in 3 independent directions. We know that our instruments, from rulers to laser interferometers, measure distances in 3 perpendicular axes. We know that the mathematics of our everyday physics, from Newton's laws to the engineering that builds bridges and aeroplanes, works beautifully in 3 dimensions. What we do not know is whether 3 dimensions are all that exist. This distinction matters enormously. The history of science is littered with confident assumptions that turned out to be limitations of perception rather than features of reality. For millennia, humans were certain the Earth was flat, not because they had evidence it was flat, but because they couldn't perceive its curvature. They were certain the stars were fixed on a celestial sphere, not because they had measured the sphere, but because they couldn't perceive the vast distances that separated individual stars. They were certain that time flowed at the same rate everywhere, not because they had tested this, but because they couldn't perceive the relativistic effects that Einstein would later reveal. In each case, what felt like direct knowledge of reality was actually a limitation of human perception, mistaken for cosmic truth. The question is, are we making the same mistake about dimensions? Think about how you came to know that space has 3 dimensions. Did you conduct experiments? Did you test alternatives? Or did you simply accept what your senses told you and what everyone around you assumed? Most likely, you never questioned it at all. 3 dimensions felt less like a discovery about the universe and more like the definition of reality itself. But now, try something. Point in every direction you can imagine. Up, down, left, right, forward, backward, and every diagonal between. Really do it. Extend your arm and trace out all the directions you can indicate. Now ask yourself, how would you know if you were missing one? This is not a trick question. It has a serious answer. If a dimension existed, but was curled so small that your finger could not enter it, you would have no sensation of its existence whatsoever. Your pointing would feel complete while being partial. You would survey the full range of directions you could perceive and conclude, incorrectly, that you had surveyed all directions that exist. Consider the ant. Imagine an ant walking along a garden hose. From far away, the hose appears to be a line, a one-dimensional object stretching from the tap to the flower bed. The ant, from its perspective on the surface, can walk forward along the hose's length or backward. That's it. One dimension of freedom. One direction to travel. But get closer to the hose, and you notice something the distant observer missed. The hose has a circumference. It wraps around. The ant can also walk around the hose, not just along it. There's a second dimension, a direction perpendicular to the first that was invisible from far away but becomes obvious up close. Here is the crucial insight. If you shrank that circumference to microscopic scale, it would still exist as a dimension, but no distant observer would ever detect it. The hose would appear perfectly one-dimensional even while secretly being two-dimensional. The extra dimension would be there, at every point along the hose's length, carrying the ant around in circles too small for any measurement to resolve. Our familiar three dimensions may be the length of a cosmic garden hose, and we may be the ants. The implications of this possibility are vertigo-inducing. Look at the space around you right now, the gap between your hand and the nearest object. You see nothing there. Empty space. Void. But if extra dimensions exist, curled at every point in space, then what you perceive as emptiness might be extraordinarily dense with hidden structure. The nothing you see might contain elaborate geometry in directions you cannot perceive. The room you occupy might harbour directions you cannot point to, and you would never know by looking. This is not mysticism or metaphor. It is the logical consequence of a simple observation. Perception is not completeness. We perceive a solid table, yet physics reveals it is mostly empty space with atoms separated by vast relative distances. We perceive continuous motion, yet quantum mechanics reveals discontinuous jumps at the smallest scales. We perceive a static universe, yet cosmology reveals everything is hurtling apart at tremendous speed. Again and again, reality has proved more elaborate than perception suggested. The universe is under no obligation to limit itself to the directions you can point to, and our senses, it bears remembering, did not evolve to reveal cosmic truth. They evolved to keep us alive long enough to reproduce. We see the wavelengths of light useful for identifying ripe fruit and approaching predators. We hear the frequencies useful for communication and detecting danger. We navigate three spatial dimensions because that is what hunting and gathering on the African savanna required. Nature equipped us to survive. It did not equip us to perceive the complete architecture of space-time. There is no reason to expect these two goals would produce the same sensory apparatus. So when we feel certain that three dimensions are all there are, we should ask, is this certainty based on evidence? Or is it based on the same cognitive confidence that once made humans certain the earth was flat, the stars were fixed, and time was absolute? The question of extra dimensions is not science fiction. It is one of the most serious questions in fundamental physics. And it begins here, in this room, with the unsettling recognition that everything you think you know about where you are might be incomplete. If extra dimensions might exist, an obvious question demands an answer. Where are they? Why have we never stumbled into one? Why, in all of human history, has no explorer returned from a journey into the fourth spatial dimension? The question assumes something that turns out to be false. It assumes that all dimensions must be alike, vast, extended, obvious to anyone who looks. It assumes that if a dimension exists, it must stretch out, like the three we know, open for exploration, available to perception. But there is no law of physics demanding this. There is no mathematical principle requiring dimensions to be created equal. A dimension can be vast, stretching billions of light years like our familiar three. Or it can be tiny, curled into a circle smaller than an atom. This is the concept of compactification, and it transforms extra dimensions from fantasy into physical possibility. Return to the garden hose. We established that it has two dimensions, the length stretching from tap to flower bed, and the circumference wrapping around. But notice something important. These two dimensions are utterly different in character. The length is extended. You can walk along it seemingly forever, or at least until you reach the tap. The circumference is compact. Walk around it, and you quickly return to where you started. Both are genuine dimensions. Both represent directions of travel. But one is extended and obvious. The other is compact and could, if small enough, become invisible. Now imagine that circumference shrunk even further, shrunk past millimeters, past micrometers, past nanometers, shrunk down to the Planck scale, roughly 10 to the power of minus 35 meters, a distance so small that a proton is to it as the observable universe is to a grain of sand. At that scale, the dimension would still exist. It would still be a direction, but it would be utterly undetectable by any instrument we have ever built or could conceivably build with current technology. The hose would appear perfectly one-dimensional to every possible measurement, even while secretly harboring a second dimension curled at every point along its length. This is how dimensions can hide, not by being elsewhere, by being everywhere, but curled so tight they escape detection. String theory, one of the leading candidates for a unified theory of physics, proposes exactly this. It suggests that our universe has not 4 dimensions, 3 of space plus time, but 10, or in some versions, 11. The 6 or 7 extra dimensions are not missing or elsewhere. They are compactified, curled into geometric shapes so minuscule that they exist at every point in the space we navigate while remaining forever beyond our perception. The specific shapes these dimensions curl into have a name: Calabi-Yau manifolds. These are geometric structures of extraordinary complexity and mathematical beauty. 6-dimensional shapes twisted and folded in ways our 3-dimensional intuition cannot visualize, but our equations can describe precisely. If string theory is correct, one of these shapes exists at every single point in space, smaller than any scale we can probe. The implications are remarkable. Look at the air in front of you. What you perceive as empty space might contain, at every single point, additional dimensions curled into intricate geometry. Geometries carrying information about why particles have the masses they do, why forces have the strengths they measure, why the universe follows the laws it follows. You would never detect them directly. The scale at which they exist is roughly 10 to the power of 20 times smaller than a proton. Our best particle colliders, like the Large Hadron Collider, probe distances down to about 10 to the power of minus 19 meters. The compactified dimensions might be at 10 to the power of minus 35 meters or smaller. The gap between our instruments and the hidden dimensions is larger than the gap between a grain of sand and the observable universe. And yet, they would be present, here, now, at every point in this room, in your chair, in the air you breathe, in the atoms of your body. Hidden dimensions would not be distant realms accessible through magical portals. They would be intimate features of the space you occupy, structure so finely grained that you carry it with you constantly without ever being aware of it. Think of it this way. Imagine you could zoom in on a single point in space, magnifying it 1 billion times, then 1 billion times more, then 1 billion times again. Ordinary intuition suggests you would find nothing special at smaller scales, just more space, emptiness repeating. But if compactification is real, at some magnification, the zoom would reveal something astonishing. Space itself opening up, revealing new directions, new geometry, hidden architecture that was there all along but too small to see. The zoom would reveal not emptiness, but structure. This is a profound shift in how we think about space. We tend to imagine space as a smooth, featureless void, a stage on which matter performs but which has no features of its own. Compactification suggests otherwise. It suggests that space itself has elaborate structure at the smallest scales, containing dimensions curled into complex geometries, shaping everything that happens within it. Space is not empty. Space is not simple. Space may be the most elaborate thing there is, if only we could see small enough to perceive its architecture. The error most people make when first encountering extra dimensions is assuming that existence requires obviousness. If they existed, the reasoning goes, we would see them. But this reasoning fails throughout physics. Atoms existed before microscopes revealed them. Radio waves existed before receivers detected them. Dark matter exists, though we cannot see it, inferred only from gravitational effects on visible matter. Existence does not require detection. Dimensions can hide. The question is not, why can't we see them? The question is, at what scale would they become visible? And are there other ways, indirect ways, to detect their presence? As we shall see, there may be. The fingerprints of hidden dimensions might appear in the most extreme environments we can probe, at the heart of black holes, in the collisions of particles at tremendous energies, in the subtle deviations of gravity at very small distances. The dimensions are hiding, but hiding is not the same as absent, and the universe, it turns out, may have been keeping secrets in dimensions curled too small for us to perceive, secrets that shape everything we see. We have seen how dimensions could exist without being obvious, curled so small they escape detection while present at every point in space. But a deeper question demands an answer. Why would physics need extra dimensions in the first place? Why not simply accept the 4 dimensions we perceive and move on? The answer lies in a crisis at the very foundations of physics, a crisis that has persisted for nearly a century, a crisis that has driven some of the most brilliant minds in history to consider possibilities that seem, at first glance, absurd. The crisis is this: our 2 most successful theories of physics refuse to work together. On one side stands general relativity, Einstein's masterwork. It describes gravity as the curvature of space-time. Mass and energy warp the fabric of the universe, and this warping is what we experience as gravitational attraction. General relativity is not merely successful, it is spectacularly, breathtakingly successful. It predicts the bending of light around massive objects, confirmed by observation. It predicts gravitational waves, detected in 2015 after a century of searching. It predicts black holes, now photographed. Its precision is extraordinary. Measurements of gravitational effects routinely match predictions to many decimal places. On the other side stands quantum mechanics. It describes the behavior of particles at the smallest scales, atoms, electrons, photons, quarks. It explains how chemistry works, why atoms are stable, how semiconductors operate, why the sun shines. Every electronic device you use, every medical imaging technology, every laser pointer works because quantum mechanics is correct. Its predictions match experiments with a precision that defies easy comprehension, in some cases to 10 decimal places. Both theories work. Both are confirmed by countless experiments. Both are among the most successful scientific achievements in human history, and they are mutually incompatible. This is not a minor technical problem. When physicists try to combine general relativity and quantum mechanics, To create a quantum theory of gravity, the mathematics produces garbage. Infinities appear where answers should be. Predictions become meaningless. The equations collapse into absurdity. This matters because the universe keeps generating situations where both theories should apply simultaneously. At the heart of black holes, matter is compressed into unimaginably small regions where gravity is extreme and quantum effects matter. At the Big Bang, the entire universe was once concentrated in a state where both theories should speak, and neither can. At the smallest scales of distance, called the Planck scale, gravity and quantum mechanics collide head-on, and our theories produce gibberish. We literally cannot describe these regimes. Our two greatest theoretical triumphs fall silent precisely where we need them most. This is the unification problem, and physicists have tried for nearly a century to solve it. String theory offers a potential resolution. Its central idea is elegant. What if the fundamental particles of nature, electrons, quarks, photons, even gravitons, are not dimensionless points, but tiny vibrating strings of energy? Consider a violin string. Depending on how it vibrates, which harmonic patterns it produces, it creates different notes. A single string produces many sounds. Now imagine that fundamental particles work similarly. A fundamental string, vibrating one way, appears as an electron. Vibrating another way, it appears as a quark. Vibrating yet another way, it appears as a graviton, the hypothetical carrier of gravitational force. In this picture, the apparent diversity of particles is merely diversity of vibration. There is only one kind of fundamental entity, the string, manifesting as different particles depending on how it vibrates, and crucially, gravity emerges naturally from the string picture. The graviton is simply one vibration pattern among many. There is no need to force gravity into the quantum framework. It belongs there from the start. This is mathematically elegant. It is conceptually beautiful. It offers hope for unification. But here is the catch. The mathematics of vibrating strings only works in higher dimensions. In 4 dimensions, 3 of space plus 1 of time, string theory produces what physicists call anomalies. These are mathematical inconsistencies that indicate the theory is broken. The equations contradict themselves. Predictions become impossible. The elegant framework falls apart. Add more dimensions, and something remarkable happens. The anomalies cancel. The contradictions resolve. The theory heals itself. Not in any number of dimensions, specifically in 10, or, with additional mathematical structure, in 11. This is not a choice physicists made because they wanted more dimensions. Quite the opposite. A 4-dimensional string theory would have been simpler, more intuitive, more easily tested. Theorists would have vastly preferred it. The equations rejected their preference. The mathematics voted, and it voted unanimously. 10 dimensions, or the theory doesn't work. Think of it this way. Imagine trying to flatten a complex origami sculpture onto a table. Some shapes can be flattened without tearing or overlapping, but others cannot. Their structure requires the 3rd dimension to exist without contradiction. Flatten them, and they tear. Keep them in 3 dimensions, and they remain whole. The unified description of particles and forces may be similarly constrained. In 4 dimensions, the theoretical shape tears itself apart. In 10 dimensions, it lies flat and consistent. The extra dimensions are not decorations added for excitement. They are the space in which a unified theory can exist without self-contradiction. This is what makes extra dimensions worth taking seriously. They are not speculation dreamed up by theorists who wanted physics to be more exotic. They emerge from demanding mathematical consistency. They are the price of unification. Nature, it seems, does not care about our preference for simplicity. The equations are quite firm. Every particle collision at CERN, every gravitational wave detected by LIGO, every measurement of quantum phenomena operates under theories we know are incomplete. The electron in your phone, the light entering your eye, the gravity holding you to Earth, all are described by frameworks that contradict each other at extreme scales. We live comfortably with this contradiction only because we rarely encounter conditions where it matters. But the contradiction is real, and extra dimensions may be part of its resolution. The question shifts. It is no longer, why would we add dimensions? It becomes, why would the universe limit itself to the dimensions we happen to perceive? If extra dimensions exist, curled at every point in space, they are not mere backdrop. They are not passive scenery, while the real action happens in the 3 dimensions we perceive. They would be active participants in everything, shaping the particles we observe, determining the forces we feel, setting the values of the constants we measure. This is perhaps the most profound implication of compactified dimensions. The hidden geometry would not be hiding idly. It would be doing something, and what it would be doing is determining the physics of the visible universe. Consider a pipe organ. Each pipe has a specific length and shape. This geometry determines which notes the pipe can produce, its fundamental frequency and overtones. Change the pipe's geometry, and you change its sound. Shorter pipes produce higher notes. Longer pipes produce lower notes. The shape of the chamber affects the timbre. If extra dimensions are curled into specific geometric shapes, those shapes may function like cosmic organ pipes. The geometry would select which particles can exist and how they behave. Different shapes would produce different particles with different masses and different interactions. The music we call physics, the symphony of electrons and quarks and photons, would depend entirely on the hidden pipes we cannot see. In string theory, this connection is precise. Particles arise from strings vibrating in the full 10-dimensional space, but how strings can vibrate depends on the shape of the compactified dimensions. The Calabi-Yau manifold at every point in space, the 6-dimensional curled geometry, acts as a kind of resonance chamber, selecting which vibration patterns are possible and which are forbidden. Different Calabi-Yau shapes would produce different particle physics, different masses, different force strengths, different fundamental constants. The implications are startling. Why does the electron have the mass it has? Perhaps because the hidden dimensions happen to be curled in a way that selects for that particular vibration pattern. Why is gravity so astonishingly weak compared to electromagnetism? About 10 to the power of 36 times weaker. Perhaps because the geometry of extra dimensions causes gravitational effects to dissipate in directions we cannot perceive. What we experience as fundamental laws may be accidents of geometry. This is humbling. We are accustomed to treating the constants of nature as truly constant, as features of reality that could not have been otherwise. The speed of light, the charge of the electron, the strength of the nuclear forces. These numbers appear in our equations as inputs, as givens, as features that must be accepted rather than explained. But compactification suggests they may be outputs rather than inputs, consequences of how extra dimensions happen to be folded rather than fundamental truths about existence. The laws of physics we observe may not be the only possible laws. They may be one set among an enormous landscape of possibilities. each corresponding to a different way of crumpling the extra dimensions. The mathematics suggests there are an unimaginably large number of possible Calabi-Yau shapes, perhaps 10 to the power of 500 or more. If each shape produces different physics, then our universe, with its specific particles and forces and constants, might be one room in an unfathomably vast mansion of possible physics. Why do we find ourselves in this particular room? That is a question without easy answer. Perhaps the geometry was set by initial conditions at the Big Bang. Perhaps there is some selection principle we have not yet understood. Perhaps our universe is one of many, each with different compactification, and we inevitably find ourselves in one compatible with our existence. These are among the deepest questions in physics. They are not yet answered, but the framework itself is clear. If extra dimensions exist, their shape determines our reality. Every fundamental constant you have ever encountered might be a geometric property of curled dimensions rather than an intrinsic feature of existence. The next time you consider a fundamental constant, the speed of light, the charge of an electron, the mass of a proton, consider that these values might be contingent. They might have been otherwise. They might be accidents of how space happens to be folded at scales too small for us to perceive. This does not make them less real. The speed of light remains 299,792,458 meters per second in our universe. Regardless of what causes it, the electron's charge remains what it is. But understanding that these constants might be geometric rather than truly fundamental changes how we think about them. It suggests that why does physics have these constants might be a meaningful question with a meaningful answer, not a mystery beyond inquiry, but a consequence of architecture we have not yet mapped. We have been trying to understand the universe while ignoring most of its architecture. The hidden dimensions, if they exist, are not empty space. They are the blueprint. A theory that cannot be tested is not physics. It is metaphysics. Perhaps interesting, perhaps beautiful, but not science. Science requires predictions that can be checked against reality, hypotheses that risk falsification. So the question becomes urgent. If extra dimensions exist, but are curled at scales far smaller than we can probe directly, is there any way to test for their presence? Or are they forever beyond observation, elegant mathematics disconnected from empirical reality? The answer offers hope. Hidden dimensions are not empirically empty. They make predictions. At extreme scales, at enormous energies, at tiny distances, in the most violent environments the universe provides, their effects should become detectable. And the most promising laboratory is one of the strangest objects physics has ever conceived: the black hole. Black holes are not merely cosmic curiosities. They are nature's ultimate compression machines, concentrating matter into regions so small that the normal rules of physics are pushed to their limits. At the heart of a black hole, mass is squeezed into a singularity, a point of theoretically infinite density, where our current theories break down completely. It is precisely at such extremes that hidden dimensions might reveal themselves. Consider how gravity works at different scales. At large distances, the distances of everyday experience, of planets and stars, gravity follows Newton's inverse square law. The force between two objects decreases with the square of the distance between them. Double the distance, and gravity falls to a quarter of its strength. This has been tested with exquisite precision at scales from millimeters to astronomical units. But if extra dimensions exist, gravity should behave differently at very small distances. Why? Because gravitational field lines, unlike those of other forces, might spread into the full dimensional structure. At scales larger than the compactified dimensions, this spreading doesn't matter. Gravity appears four-dimensional. But at scales comparable to the extra dimension size, gravity would suddenly have more room to spread. It would grow stronger than the inverse square law predicts. This deviation would be a fingerprint, a signature that something is happening at small scales that our four-dimensional theories don't expect. Experiments are searching for exactly this. Physicists have measured gravitational forces at distances down to approximately 50 micrometers, about the width of a human hair, finding no deviation from Newton's law. This tells us that if extra dimensions exist, they must be curled smaller than 50 micrometers. The search continues at ever smaller scales. Particle colliders offer another window. At the Large Hadron Collider, protons collide at energies that momentarily concentrate vast amounts of energy into minuscule regions. If extra dimensions exist and are larger than a certain threshold, these collisions could have observable consequences. One dramatic possibility: microscopic black holes. In 4 dimensions, creating a black hole requires compressing mass beyond a threshold called the Schwarzschild radius. For an object of Earth's mass, this radius is about 9 millimeters. For the energy available in particle collisions, the corresponding radius is so fantastically small, roughly 10 to the power of minus 52 meters, that black hole formation is completely impossible. But if extra dimensions exist, gravity becomes stronger at small scales. The threshold for black hole formation drops. Microscopic black holes might form at energies accessible to our colliders. These black holes would not be dangerous. They would evaporate almost instantly through a process called Hawking radiation, the quantum effect by which black holes slowly radiate away their mass. But their brief existence would produce distinctive signatures, sprays of particles in unusual patterns, characteristic energy distributions, evidence that something profound happened in that collision. No such signatures have been observed. This tells us something important. If extra dimensions exist, they are not large enough or accessible enough for current colliders to reveal them. The absence of evidence constrains the possibilities, narrowing the range of compactification scenarios that remain viable. But absence of evidence is not evidence of absence. The dimensions may simply be hiding at scales even smaller than we can currently probe. The experiments continue. There is another way black holes might reveal extra dimensions: through their radiation spectra. A black hole emitting Hawking radiation produces particles of various types and energies. The precise mix depends on the number of dimensions the black hole exists in. A black hole in 10 dimensions would radiate differently than one in 4. If we could observe the Hawking radiation from black holes directly, perhaps from primordial black holes left over from the Big Bang, if they exist, we might detect dimensional signatures. The challenge is that Hawking radiation from stellar mass black holes is unimaginably faint, far beyond any foreseeable detector. But the theoretical framework exists, and the prediction is clear. The question of extra dimensions is not metaphysical, it is empirical. Every gravitational measurement at small scales, every particle collision at high energies, every observation of black hole behavior is potentially a test of dimensional structure. The universe has been asked the question. Experiments are running right now. Physicists are searching for signatures that would confirm or constrain the existence of hidden dimensions. If the universe has hidden dimensions from us, it has done a remarkable job. Then again, The universe has had 13.8 billion years to practice, but hiding is not permanent. We have found atoms that were hidden for millennia. We have detected gravitational waves that were hidden since the dawn of time. We have photographed black holes that were once considered too extreme to ever observe. The hidden dimensions, if they exist, are not safe from inquiry. Science is patient, and science is persistent. The universe may be keeping secrets, but we are learning how to ask the right questions. We have traced extra dimensions from conceivability through mathematical necessity to empirical testability. We have seen how they could hide, why physics might need them, and how experiments might detect their fingerprints. But we have not yet confronted the deepest question, the one that touches not just physics, but existence itself. If extra dimensions exist, if we perceive 4 dimensions of a 10-dimensional reality, what does that make us? The answer requires a shift in perspective. And the best way to achieve that shift is to imagine beings more limited than ourselves. Consider a creature living on a perfectly flat plane, a 2-dimensional being in a 2-dimensional world. This is not a new thought experiment. The Victorian schoolmaster Edwin Abbott explored it in his 1884 novella Flatland, but its implications remain profound. This creature, call it a flatlander, perceives only length and width. Height is not merely invisible to it. Height is inconceivable. The flatlander has no sensory apparatus for the 3rd dimension, no words in its language, no concepts in its mind. Ask a flatlander to point upward, and it cannot comply. Not because it is stubborn, but because upward has no meaning in its perceptual framework. Now imagine you, a 3-dimensional being, approach this flat plane and poke your finger through it. What does the flatlander see? It sees a circle appear from nowhere, a mysterious disk, materializing without explanation. If you push your finger further through, the circle grows larger. Pull back, and it shrinks. Withdraw entirely, and it vanishes as mysteriously as it appeared. The flatlander is utterly baffled. Where did this circle come from? Where did it go? The appearance and disappearance seem like magic, like violations of natural law. But there is no magic. There is simply a dimension the flatlander cannot perceive. Your finger, extended in 3 dimensions, intersects the flat plane as a 2-dimensional cross-section. The circle the flatlander sees is real. It can be measured, touched, interacted with. But it is incomplete. It is a slice of something more comprehensive, something extended in a direction the flatlander cannot conceive. Now consider the implications for us. If reality has 10 dimensions and we perceive 4, we are flatlanders of a sort. Everything we experience, every particle, every force, every event, might be a lower dimensional cross-section of a higher dimensional reality. The objects we call fundamental might be intersections of higher dimensional structures with our limited perceptual plane. This is not metaphor, it is geometry. Think about what a higher dimensional perspective would reveal. You, looking down at Flatland, see everything the flatlander considers hidden. You see inside its closed rooms. You see the interiors of its bodies. You see its entire world laid out before you, simultaneously, with nothing concealed. A being perceiving more dimensions than we do would have an analogous advantage. It would see aspects of our existence that we consider private or hidden. It might see our interiors not through X-ray technology, but simply because the structures we consider enclosed are open from higher dimensional vantage points. It might see our entire timelines, past, present, and future, laid out as static shapes, the way we see the full length of a worm rather than just one cross-section at a time. our privacy, our hiddenness, our sense that some things are truly concealed. All of this might be parochial, features of our dimensional limitations rather than features of reality itself. This possibility raises questions that venture beyond physics into philosophy. What is observation? What counts as an event? Are there perspectives from which questions we consider open are already settled, where outcomes we experience as uncertain are already determined and visible? These questions have no easy answers, but they emerge naturally from taking the geometry of extra dimensions seriously. Consider, too, what we ourselves might be. You experience yourself as a complete entity, a body with boundaries, a mind with contents, a person with history and future. But if extra dimensions exist, there may be more to you, structure extending in directions you cannot perceive, aspects of your existence playing out in dimensions you cannot access. Look at your hand. What you see is a three-dimensional object extended through time. You perceive its surface, its shape, its motion. But if extra dimensions exist, your hand might extend into them as well, carrying structure you have never sensed, geometry you have never perceived, activity you have never noticed. This is not mysticism. It is the logical consequence of dimensional geometry. A shadow is real. It moves, it has shape, it can be measured, but it contains less information than the object casting it. A shadow is a lower dimensional projection of a higher dimensional form, faithful in some ways, incomplete in others. If extra dimensions exist, we may be shadows of a sort, not unreal, not illusory, but partial, cross-sections of something more comprehensive, projections of structures extended in directions we cannot see. The universe might be larger than we knew, and we might be smaller, not in significance, but in completeness. This is humbling, but humility in the face of cosmic complexity is not humiliation. It is accuracy. It is the proper response to recognizing that our perceptual apparatus evolved for survival on a small planet, not for comprehensive awareness of reality's full architecture. We are remarkable creatures nonetheless. We have deduced the possible existence of dimensions we cannot perceive. We have written equations describing structures we cannot directly observe. We have asked questions that transcend our sensory limitations through the power of mathematical reasoning alone. If we are shadows that have learned to wonder about the light. There is a question that sounds fanciful, but is mathematically serious. If extra dimensions exist, what is happening in them right now? The instinct is to dismiss this as unanswerable, or worse, as meaningless. How can we ask about activity in dimensions we cannot perceive? How can we investigate phenomena in realms we cannot access? But the question is not meaningless. If extra dimensions exist, they are not empty voids. They are not static backdrops. They are dimensions, directions in which things can happen. Fields can fluctuate, particles can propagate, physics can unfold. And there are hints about what might be happening there. Consider gravity, the most familiar and yet most mysterious of forces. We experience gravity constantly. It holds us to the Earth, keeps the moon in orbit, binds galaxies together. It is everywhere and always. Yet gravity has a peculiar property that has puzzled physicists for decades. It is extraordinarily weak. This weakness is not obvious in everyday experience. Gravity feels strong enough when you drop something or climb stairs, but compare gravity to the other fundamental forces. Electromagnetism, which governs the behavior of charged particles, is about 10 to the power of 36 times stronger than gravity at the scale of individual particles. That is a 1 followed by 36 zeros. The strong nuclear force, which holds atomic nuclei together, is even more powerful. Gravity is the weakest force in nature by an almost inconceivable margin. Why? In 4 dimensions, this is simply an unexplained fact, a feature of nature that must be accepted as given. But in higher dimensional frameworks, an explanation emerges. Imagine a fish in an aquarium. The fish swims freely through 3 dimensions of water, left and right, forward and backward, up and down. But it cannot leave the water. It cannot explore the room surrounding its tank. From the fish's perspective, the tank is the entire world. Now imagine the room is active. People walk through it. Conversations happen. Light changes as the sun moves across the sky. All of this activity is invisible to the fish, occurring in spaces it cannot access, affecting it only indirectly. If extra dimensions exist, we may be fish. Some theoretical models propose that the forces we experience, electromagnetism, the weak force, the strong force, are confined to our 4-dimensional tank. They cannot spread into the extra dimensions. They are stuck on what physicists call a brane, short for membrane, a lower dimensional surface embedded in a higher dimensional space. But gravity, in these models, is different. Gravity is the curvature of space-time itself, and space-time includes all dimensions, not just the ones we're stuck on. Gravity can spread into the extra dimensions. Its influence can leak away into directions we cannot follow. If this is true, gravity's mysterious weakness is explained. Gravity is not intrinsically weak. It only appears weak to us because most of its influence dissipates into dimensions we cannot perceive. We feel only the small fraction that remains in our 4-dimensional experience, like hearing only the faintest echo of a concert happening in a room we cannot enter. Every time you lift an object against Earth's pull, you might be overpowering a force that is mostly elsewhere, mostly spreading through dimensions you cannot access, mostly happening in directions you cannot point to. Gravity's weakness may be evidence of extra dimensions operating right now, but gravity is not the only thing that might be happening in extra dimensions. If they exist, quantum fields extend into them, the same fields that give rise to particles in our 4 dimensions. These fields fluctuate constantly, even in apparent vacuum. In extra dimensions, those fluctuations continue, invisible to us, but potentially influencing our reality in subtle ways. There might be particles propagating through extra dimensions, particles that feel only gravity and therefore interact only weakly with our ordinary matter. These would be invisible to our detectors except through their gravitational effects. Some physicists have speculated that dark matter, the mysterious substance that makes up about 27% of the universe's mass energy but has never been directly detected, might be matter in extra dimensions, revealing itself to us only through gravity. This is speculation, not established fact, but it is scientifically motivated speculation, the kind that leads to testable predictions and eventual experimental resolution. The hidden dimensions would not be passive storage space. They would be arenas of activity, fields fluctuating, forces spreading, perhaps particles moving, perhaps entire ecologies of physics playing out in directions we cannot perceive. At every point in space, at this very moment, something might be happening in dimensions we cannot see. Activity as real as the activity in the room surrounding the fish's tank, but forever beyond our direct perception. The universe may be far busier than it appears. We see 3 dimensions of space. We move through 1 dimension of time. We catalogue the particles and forces we can detect and call it physics. But the full reality, if extra dimensions exist, includes activity we can never directly witness. The room extends beyond the tank. The concert continues beyond the echo. We experience our slice. The cosmos may be vastly more. If extra dimensions exist, humanity has spent its entire history exploring a hallway, while a mansion extended in directions we could not turn toward. This is not a diminishment, it is an expansion. Consider the hallway. We have studied it with extraordinary care. We have mapped its paintings, the particles and forces of the standard model, catalogued with precision. We have measured its dimensions, the 3 directions of space we can perceive, the flow of time we experience. We have understood its construction, the laws of physics that govern everything we see. The hallway is real. Its contents matter. The knowledge we have gathered is genuine. But the mansion may be larger than we knew. Imagine visitors to a great house who have spent generations studying a single corridor. They know every painting on its walls, the colours, the brushstrokes, the frames. They know the pattern of the carpet, each thread accounted for. They know the light that enters through the windows, its angle throughout the day, its spectrum at dawn and dusk. They have catalogued everything within reach, understood the principles governing what they can see. Then someone notices something strange. The hallway's proportions suggest it is part of something larger. The architecture implies rooms extending beyond the walls. The way sound echoes hints at spaces not visible from where they stand. No doors are apparent, but the evidence suggests the house does not end here. This discovery does not invalidate what they have learned. The paintings remain beautiful. The carpet remains intricate. The light remains fascinating. Everything they understood about the hallway is still true. But the hallway is not the whole house. This is our situation if extra dimensions exist. We have learned a great deal about the universe as we perceive it. Quantum mechanics predicts particle behavior with astonishing accuracy. General relativity describes gravity's effects with extraordinary precision. Chemistry explains how atoms combine. Biology explains how life evolves. Neuroscience illuminates how brains function. The hallway is richly understood, and it may be part of something larger. Mathematics has reached beyond perception. We have deduced the possible existence of dimensions we cannot see, not through magic or revelation, but through the same methods that revealed atoms, predicted black holes, and detected gravitational waves. Human reasoning has transcended human sensation. This is remarkable. We are creatures whose eyes evolved to spot ripe fruit, whose ears evolved to detect approaching predators, whose sense of space evolved to navigate the African savanna. Nothing in our evolutionary history prepared us to deduce the structure of space-time at scales 10 to the power of 20 times smaller than a proton. Yet here we are, writing equations about extra dimensions. If they exist, they represent not the limits of human understanding, but the extension of it. We have figured out that the house might be larger than the hallway. That we cannot walk through walls into the other rooms does not diminish the achievement of recognizing they might exist. Every expansion of our understanding has followed this pattern. We once thought the Earth was the center of existence, then discovered we orbit an ordinary star. We once thought the Milky Way was the entire universe, then discovered it is one galaxy among hundreds of billions. We once thought space and time were absolute, then discovered they warp and weave together. We once thought the vacuum was truly empty, then discovered it seethes with quantum activity. Each expansion was initially disorienting. Each eventually became a source of wonder rather than despair. Extra dimensions continue this magnificent tradition. The universe is not obligated to fit our intuitions. It is under no requirement to match the expectations of creatures whose brains evolved for hunting and gathering. When reality proves stranger than common sense suggests, the appropriate response is not disappointment, but awe. We find ourselves in a cosmos that may contain architecture beyond our perception, and we have managed, through pure thought and mathematical reasoning, to glimpse its possibility. This is not humiliation. This is dignity. The hallway is beautiful, and the mansion, if it exists, is beautiful too. We may never walk through all its rooms, but we have stood in the hallway and deduced that it might be part of something more. That is not a small achievement for an advanced breed of monkeys on a minor planet of a very average star. We began with a room, a perfectly ordinary room. 4 walls, a floor, a ceiling. 3 directions you could point to. Time ticking on the clock. Everything about where and when you exist, described completely. Or so you believed. We have travelled far from that certainty. We have seen that our confidence in 3 dimensions is based not on evidence, but on the limits of perception. We have learned that dimensions can hide, curled so small they escape detection, while present at every point in space. We have discovered that mathematics demands extra dimensions, not as decoration, but as the price of consistency. We have understood that hidden geometry might shape everything we see, determining particle masses and force strengths through architecture we cannot probe. We have confronted the possibility that we are shadows, cross-sections of higher dimensional reality, experiencing part while the whole extends in directions we cannot perceive. We have asked what might be happening in dimensions we cannot access, and found that the answer might include the very weakness of gravity itself. We have stood in the hallway and wandered about the mansion. Now we return to the same 4 walls, floor and ceiling, the same 3 directions you can point to, but you are not the same. The room has not changed. Your understanding of it has. What seemed complete now seems possibly partial. What seemed obvious now seems like hypothesis. What seemed like the definition of reality now seems like the limits of perception. This is the transformation that genuine understanding brings. Not new facts added to old certainties, but old certainties dissolved into deeper questions. The question of extra dimensions is no longer science fiction. It is science. Experiments are probing it. At laboratories around the world, physicists measure gravitational forces at ever smaller scales, searching for deviations that would signal hidden dimensions. Particle colliders accelerate protons to unprecedented energies, watching for missing energy signatures or microscopic black hole formation. Gravitational wave detectors listen for ripples that might carry dimensional fingerprints. Mathematics demands it. String theory, one of the most promising approaches to unifying all of physics, does not function in 4 dimensions. The equations break, add extra dimensions, and they heal. This is not speculation. It is mathematical necessity. Theorists did not choose extra dimensions because they wanted them. The equations insisted. The universe keeps pointing toward it. Gravity's inexplicable weakness, the fine-tuning of fundamental constants, the incompatibility of our 2 greatest theories, all of these might find resolution in higher dimensional frameworks. The universe seems to be hinting at structure beyond what we perceive. Return to the garden hose one final time. From far away, it appeared to be a line, a simple one-dimensional object. But closer examination revealed a hidden dimension, the circumference that was there all along, curled too small to see from a distance. What seemed complete was partial. What seemed fully understood was incompletely perceived. The hose taught us that reality can contain more than we see, and that recognizing this limitation is the first step toward transcending it. We may be at that moment of recognition. The room you occupy right now might contain dimensions curled beyond detection. Every point in space might harbor elaborate geometry in directions you cannot point to. The mystery might be not in distant galaxies, but in the air around your hand. The hidden dimensions, if they exist, are not elsewhere. They are here, at every location you have ever occupied, intimate, immediate, present, and yet invisible. Tomorrow, when you walk across this room, consider that you may be walking through dimensions you cannot enter. When you lift an object, consider that gravity's weakness might be evidence of forces leaking into hidden directions. When you look at empty space, consider that it might be densely structured at scales beyond your perception. Let the question accompany you: what else is here? This is not mysticism. It is physics. It is the recognition that our perceptual apparatus evolved for survival, not for completeness. It is the acknowledgement that mathematics can reach where senses cannot. It is the understanding that reality has consistently proved more elaborate than intuition suggested. The story is not finished. We do not yet know if extra dimensions exist. The experiments are running. The mathematics is being refined. The universe has been asked, and we await its answer. This is science in motion, not settled doctrine. The question is open. The inquiry continues. The answer may come in our lifetimes, or it may take centuries. But the question itself is no longer dismissible as fantasy. We have learned throughout history that reality exceeds expectation. The earth was not flat. The sun was not the center. Time was not absolute. The universe was not static. Again and again, the cosmos has proved stranger than the assumptions we brought to it. Extra dimensions may be the next item on that list, or they may not. Perhaps the mathematics will find another way. Perhaps the experiments will rule them out. Perhaps the universe will answer no. But the question is real. The inquiry is serious. The possibility is genuine. Look around the room once more. Ask yourself what else might be there. Then consider. The question is no longer science fiction. It may be the next great science fact. And that, to those of us who spend our lives asking how and why, is the best kind of question. The kind whose answer might expand everything we thought we knew about where we are, what we are, and what else might be sharing this magnificent, bewildering, surprisingly structured cosmos with us. We are just an advanced breed of monkeys on a minor planet of a very average star. But we can ask questions that transcend our perceptions. We can write equations that describe what we cannot see. We can reason our way toward truths our senses will never confirm directly. That makes us something very special. Look up at the stars tonight. Remember that you cannot see most of what is out there. Dark matter, distant galaxies beyond the observable horizon, the cosmic microwave background that fills all of space. Yet knowing these exist changes how you understand the universe. Now look at the space around you. Consider that you may not be perceiving most of what is here either. The hidden dimensions, if real, are not far away. They are where you are, right now, at this very moment. The mystery is not remote. It is intimate. The universe keeps its secrets well, but not, perhaps, forever.